Hi everyone. Today I want to tell you about the two-dimensional wave equation and how we can model two-dimensional membrane surfaces that are vibrating using a differential equation. Okay, so this is going to be very similar to the one-dimensional wave equation that we've already talked about that we use to model the vibration of a string. Right? So like a string of a guitar, you want to understand how it vibrates. We know that we can understand that motion as the solution of a partial differential equation, which was the wave equation we've been studying. But now you should think of a two-dimensional surface. You should think, for example, of a drum. And if you hit a drum, the membrane, right, in this drum will vibrate and produce a sound. But the motion of the membrane can also be described with a wave equation. So this is what we're going to talk about today. This will also model the Chladni plates that I showed you before, these metal plates with a light layer of sand on top, and as you vibrate them, these curves start to form on the plates, and we can understand these curves as well through this differential equation. In any case, we're going to start by solving this equation. In this video, we're going to compute the modes for the equation using separation of variables. And in the next video, we will learn how to solve initial value problems for it. Okay, so I'm going to start by recalling the one-dimensional wave equation first. So, recalling the one-dimensional wave equation. So in one dimension, we had a string of length L, and at any given time, so there was the variable t, which was time, and the variable x, which was the position on the string, position along the x-axis, I should say. And at every time, if you fix the time and you look at what the string looks like, so we could draw the string. Let's talk about a string that's fastened at the endpoints. Right? The string we model by the graph of a function of this variable x, right? And if you plot this is going to be a graph of some function of x, but at every point in time, you're going to see a different graph, right? And so what we model this problem by is a function utx, right? Well, if you fix the time t, you get a function of x, and that graph describes. Right? So fixing t, the graph of utx describes the strings at the string. Describes the string at that moment in time. Yeah, and we talked about the physics of this problem, and we saw that this function utx had to satisfy a partial differential equation, yeah, which we call the wave equation. So I'm going to call it the 1D wave equation, one-dimensional. Was partial t squared of u is equal to c squared partial x squared of u. C squared was a constant. C, I believe, was square root of t over rho, where t was the tension on the string and rho was the density. But it's not very important right now, so it relates to the density. So this c is some coefficient that relates to the density of the string and how tight it is fastened. Right? And our boundary conditions, we're gonna say that this string is fastened at the ends, right? So the endpoints don't move. So for all time t, at position x equals 0 and at position x equals L, u is equal to 0, so it's not moving. And let's leave it like this. I could give you an initial wave profile for the string and an initial velocity profile to solve an initial value problem. But right now we're just going to find the modes of this equation. So let's just get the partial differential equation and the boundary conditions. Okay. Let me put some color in this. Right, so that's the 1D wave equation. Now we want to talk about the two-dimensional version of this equation. Let me also make this A little prettier at that time. So let's talk about the two-dimensional version of this equation. The setup is going to be quite similar, but the difference now is instead of having one variable x to describe the string, right, the dimension of the string, now we're going to have a membrane which is two-dimensional, and so we're going to need two variables to describe the membrane, right? So okay, let me now talk about the setup for the two-dimensional wave equation. Setup for 2D wave equation. It's a similar setup. So now we have a membrane, and we're gonna talk about a rectangular membrane to start with. So I should say a rectangular membrane or a rectangular plate, if you want to think of Chladni plates. But later we can talk about different shapes as well. What if the membrane is not rectangular, it's circular, for example, it forms a disc like a drum, it's more commonly circular. Or if it's an ellipse, if the circular is not perfect, is a little stretched. And how does that alter the solutions of this equation? It alters the pitches that the drum can produce, and it alters the curves that are produced in the Chladni plates. In any case, we'll start with a simple case, which is the case of a rectangular plate or a rectangular membrane. In that case, we can model this by, now we have an x-axis and a y-axis. The x-axis has some length, I'm going to call that A. The y-axis has a certain length called B, and we can describe this membrane, rectangular membrane, by a little rectangle like that, right? So at rest it looks like that, but then it's going to start vibrating, so we need a new dimension. And there's going to be now three variables. The variable t is still time, but now the variable xy defines the position in this rectangle. But at every time now, this is gonna start vibrating. It's gonna, if this is a membrane or if it's a plate will definitely vibrate a lot less than the membrane of a drum, but they both vibrate. And then you see this surface forming, right, as it vibrates. Now this surface is gonna be the graph of a function just like before, but now this function has variables t, x, and y. And if we fix the time t, then the graph of u, t, x, y describes the membrane at that time, right? Right? Very similar. And now you might ask, okay, so you think about the physics of this problem. Can you choose any function u, t, x, y, and will it describe the motion of a membrane? And it turns out that that's not true. The functions u that you see that represent a physical motion, they are very special functions. And what we find by thinking about the physics of this problem is that the functions that represent the motion of a membrane, they have to be solutions of a differential equation, the two-dimensional wave equation, right? So u t x y must be a solution of the 2D wave equation the 2D wave equation. This is a very similar equation. Partial t squared of u is equal to c squared. And what you see here is not just the second derivative in x anymore. Now we have the variables x and y. What you see is the Laplacian of u. Right? Just like with the heat equation. You remember in the heat equation, the second derivative in x turned into a Laplacian when we solved it in 3 dimensions. That's exactly the same process that happens here. But now we need to figure out some boundary conditions to compute the modes. We could not leave any boundary conditions, then there will be really a lot of modes of this problem. But to make this well posed and have uniqueness of solutions and such, we need to impose some boundary condition. We're going to impose the condition that u for all time t, and I'll say here x y is equal to 0 for xy in the boundary of the rectangle. Okay, so that's the problem. Right, and so this is actually not a good picture for this problem that I just wrote, because you see that the surface is not still at this part of the boundary of the rectangle. Although here it is fine, it's not vibrating, but it's vibrating at this part of the boundary, which is, so it wouldn't be a solution of this problem, but it's a good picture for, it's hard to draw something more complicated than this. But this is the problem we're going to solve, right? So, and for as a reminder, what is the Laplacian of u? The c squared is just a number again. So c is a number. It depends on the density of this membrane, right? And it depends on how tightly it is fastened. But the Laplacian is a second derivative in x plus a second derivative in y of the function. Right? That's what the Laplacian operator is. It's the divergence of the gradient. You can write it like that as well. The divergence of the gradient of u. So sometimes they write it as a this symbol is called nabla. They write it as nabla squared sometimes. It's the same thing. Anyway, so and xy in the boundary of the rectangle, what does this mean? What are the points in the boundary? Let me be very specific. These are points where either see this part of the boundary here in the back is when x is equal to 0, right? So points of the form 0, y for y is always between between 0 and between 0 and b. Or over here in the front, these are points where the x coordinate is equal to a, right? So points of the form a, y, and y could be anything. Then there's this back edge here in the boundary. Those are points where y is equal to 0. So we also have that part of the boundary where y is equal to 0. So x, 0 for x between 0 and a. And then there's this part of the boundary here. That's all the points that have y equals to b, right? Y coordinate equals to b. So these are points x comma b for x between 0 and a. Right? So those are all the components of the boundary. If eventually we might need to think about this. Okay, so let's just solve this problem. So let's compute the modes. Computing the modes of this boundary value problem. Okay, so how do we compute the modes? We just apply separation of variables again. So apply separation of variables method. But we have to be a little bit clever, or just do an extra step in this problem, because there are 3 variables. So before we were separating the t variable and the x variable. Now there are 3 variables to be separated. So we need to do this in 2 steps. We're going to start by looking for solutions of the form so u t x comma y. So g of t, a function of just time, times a function f, which now is going to be a function of x and y. Okay, so first we're separating the time variable from the spatial variables. Okay, so we look for a solution of this form. And we proceed just like we usually do. We take this now, if u has this expression, you can plug it into the wave equation and see what equation we get. So on the left side, we have the second derivative in time of u. When you take a second derivative in time of this function, it only takes derivatives of g, right? So the wave equation is going to look like g dot dot of t times f x y is equal to c squared. And now Laplacian of u. This is a derivative in second derivative in x plus a second derivative in y. So what happens here, if we write slowly, a second derivative in x is only going to take a second derivative in x of f, right? Because g doesn't depend on x. So this is going to look like g of t times the second derivative in x of f of xy plus a second derivative in y of f. Yeah, I don't need this parenthesis here actually. Alright, so this is how the equation looks like right now after we took into account that u has this form. Right? It looks like this. This, by the way, this is the Laplacian of the function f, right? So just to make it a little prettier to write, this is going to look like g dot dot t f x y is equal to c squared g of t Laplacian of f of xy. Right? And just like before, with this method of separation of variables, we divide by the function u, or by g times f on both sides. Divide by g of t f of xy on both sides. So on the left side, the f's will cancel. We're gonna get g dot dot of t divided by g of t. On the right side, oh, and let me take the c squared as we usually do and send it to the left. I'll put it over here, c squared. Now on the right, we have the Laplacian of f on top. This g of t will cancel when we divide by g of t f. We're just going to get an f on the bottom. Yeah, so this is the equation now. We have to assume that g of t is not 0 and f of xy is not 0 for us to divide, but let's not think too hard about this. What we can say now, just as before, this function on the left is a function of time. Yeah? And it's equal to this function on the right. But this function on the right does not depend on time at all, right? So this function on the left is a function of time that does not depend on the time variable t, right? So a function that doesn't depend on the variable has to be a constant function, right? It assigns the same value, the same number, no matter what t is, right? So this, again, is equal to a constant. I'm still going to call it k, okay? K. This is going to be a constant. And now we can match these up, right, to get one equation, and these to get another one. So we get a differential equation for f and one differential equation for g. The differential equation for f is Laplacian of f of xy is equal to k times f of xy. And the equation for g is that g dot dot of t is equal to k times c squared g of t. So now we separated the variables. We have one differential equation for t, a different differential equation involving x and y. But once we separated the variables once, we still have a partial differential equation in our hands, right? So usually in one dimension, this partial differential equation after separating variables turned into two ordinary differential equations that only depend on one variable. But now, of course, there are three variables, so this is a nice ordinary differential equation that we can solve. But this one is a partial differential equation. We need to do something about this. Solving it is not quite easy or straightforward, but what we can do is apply separation of variables again. To separate the variables x and y. So we need to take one more step here. We need to solve this. So we're going to focus on f like before. We're going to get g after we're done with all of this stuff. We need to see how the boundary conditions are going to restrict the values of the constant k. The boundary conditions are, again, only going to affect the function f. Okay? And now that we know a little bit more about symmetric operators, I also want to point out that this is an eigenvalue, an eigenfunction equation, right? This operator, the Laplacian operator, is symmetric. With the boundary conditions that we imposed, is symmetric. Is a symmetric operator, I should say. Is a symmetric operator. Okay? And this is an eigenfunction equation for the Laplacian. We're trying to solve for the eigenfunctions of the Laplacian. This is just it's not quite important for the process, but it's just so you understand how these concepts of eigenfunctions and symmetric operators show up naturally in these problems, right? So anyway, let's focus now on f. F. Okay, so we're going to separate variables again. Separating variables. We're going to assume that f of xy is equal to a function of x times a function of y. So the function of x I'm going to call p of x. The function of y I'm going to call q of y. Okay? Now we take this form for f and we plug into the equation that we're trying to solve. All right. So you look at this equation. The Laplacian remembers the sum of second derivatives. Yeah. Here's what the Laplacian is. So what is the Laplacian of f? That's partial x squared f plus partial y squared f. But now if f has this shape, when you take the second derivative in x of f, it only takes derivatives of p, right? So the second derivative in x of f is p prime prime times q. Plus, the second derivative in y will only take derivatives of q, right? Because p doesn't depend on y. Right? So the second derivative in y of f is going to be p q prime prime. Right, so this is the Laplacian of f. And our differential equation is that the Laplacian of f, so p prime prime x qy plus px q prime prime y is equal to k times f, which is p. Oops. P times q. We divide on both sides again. We divide both sides by f, or p times q. And what we get, well, in p prime prime times q, the q's will cancel, right? So that turns into p prime prime of x divided by p of x. On p times q prime prime, the p's will cancel. Yeah, we're going to be left with q prime prime of y divided by q of y. And on the right, everything cancels. We're just left with k. Okay, and we want to make a similar argument that these functions have to be constant, or these quotients have to be constant. So what I can do is just send 1 to one of the sides. So I'm going to write p prime prime x over px is equal to k minus q prime prime y over qy. And now you see on the left we have a function of x. On the right we have a function of y. So if this function of x cannot depend on x, right? Because it's equal to this function that depends on y. And so this function must be constant. So this is equal to a constant again, is equal to, and I need to give it a different name. It's a different constant. I'll call it L. L, a constant. Okay, and we get two equations, one by matching these two up, and another one by matching these two up. The equation, one more page. The equation for P, let's see, this page break is a little annoying, but the equation for P is going to be, let's see, P prime prime of x is equal to LP of x, yeah, LP of x, and if you match these two up, you get this, q minus q prime, k minus q prime prime over q is equal to L. And then I'm going to send q prime prime to the right and L to the left. Okay, k minus L is equal to q prime prime over q. Yeah. And then you multiply by q on both sides, you get the equation q prime prime of y is equal to k minus L times q of y. Now these are two ordinary differential equations. We know how to solve these. Okay? And in fact, we'll see these are going to be two harmonic oscillators. As always, they come back. Especially if you're trying to study vibrations, but they show up in many systems. Okay, so we need to solve these equations. And the boundary conditions are really going to restrict what k and the constants k and the constant l can be. Right? So remember, so let's now analyze the boundary conditions and see how they affect p and q. Right? So now let's consider the boundary conditions. Yeah, so and we're looking for non-trivial solutions, right? So we're trying to find these modes. So we know that u of x, u of txy is equal to 0 for all possible t in R, any real number, right? T in R, and xy on the boundary of the rectangle. So first, we can write u as g of t times f of xy. Right? So this has to be equal to 0 for all t and xy on the boundary of the rectangle. And as long as we know, so for non-trivial solutions, we can assume that g of t is not the zero function, which means that there is some time, I can call it t star, such that g is not 0 at that time. Right? And if that's the case, and this equation has to be true for all possible choices of time, it must be that f of xy is equal to 0. For any xy in the boundary. Of the membrane or rectangle. Okay, so very similar to before, but now the boundary has these 4 components, and analyzing, so now that we have the f of xy is equal to 0 along the boundary, xy on boundary, we want to understand, remember we're trying to solve for f now, which means that we need to find the p and q, right? So we need to understand how this function f being equal to 0 will affect p and q. So this means that p times q is equal to 0, okay? For x and y on the boundary. And we need to consider the different components of the boundary again, right? We need to break up the components of the boundary to analyze this a little bit better. So let me remind you, the boundary has points of the form when x is equal to 0. Maybe I should write a picture, draw a picture. Here's x and here's y, and our rectangle has length a along x and length b along y. It looks like a square, but a and b don't have to be the same. So points in the boundary are points of the form, I apologize, 0, y, or x could be equal to a, right? So that gives you this left side. The right side is when x is equal to a, y can be anything. The bottom is when y is equal to 0, x can be anything. And the top is when y is equal to b and x can be anything. These different parts are going to give us different equations, right? So when p of xy is equal to 0 for all choices of xy on the boundary. Okay, so this means that p0 qy is equal to 0. Pa qy is equal to 0. px q0 is equal to 0 and px qb is equal to 0, right? So these are, I'm just matching for points of this form, that's what this equation says. Points of this form, that's what that equation says, and so on. Okay, so for non-trivial solutions, right, for a non-trivial solution, we can assume that p of x is not the zero function and q of y is not the zero function. Because if one of them is the zero function, meaning it assigns the value 0 no matter what the variable is, then the function f is going to be equal to 0, right? Because it's just a product of these two things. If the function f is equal to 0, then the function u is 0 because u is g times f. And so we found the trivial solution, right? So for a non-trivial solution, we can assume that these functions are not the zero functions, which means that there is some value of x star, that I know that p is not 0 at that value, and there's some value of y, we'll call it y star, such that I know that p is not 0 at that value, right? And if you use this property in these equations here, for example, this has to be true, p0 qy has to be equal to 0 for all choices of y. In particular, oh my god, I'm so sorry. This should be a q. Q of y star, yeah, I apologize. So q of some point y star is not 0. So this has to be 0. P0 times qy is equal to 0 for all choices of y. In particular, I can choose y equals the y star that I know, right? So here, yeah. And so I can deduce that p of 0 must be 0, right? Because the q of y star is not, and two numbers that multiply to 0, one of them must be 0, right? So what we find is that p of 0 has to be 0. On the second equation again, you know that pa times qy is equal to 0 for all choices of y. But I know that there's a choice that makes q of y not 0, right? The choice y equals y star, right? So pa qy star is equal to 0. I know that qy star is not 0, so pa must be equal to 0. Here you see that px times q0 is equal to 0 for all choices of x. If I choose the x star that I know that makes this value not equal to 0, it must be true then that q of 0 is equal to 0. And lastly, q of b has to be equal to 0, right? Same argument. What we find then are boundary conditions for p and q, right? And so we have two boundary problems. P prime prime of x is equal to, I believe it was L. Yeah, L and k minus L. Is equal to L times P of x. P of 0 is equal to P of A is equal to 0. And Q prime prime y is equal to k minus L q. Q of 0 is equal to Q of B is equal to 0. Okay? Two boundary value problems that we have seen how to solve before. Let me make sure that this is a k minus L. Yeah, k minus L. Okay, don't want to mess anything up. All right. So we have seen the solutions of this problem before, right? So we know that for non-trivial solutions, this constant L must be equal to negative n pi over a squared for n some integer greater or equal to 1. Let me add a new page anyway. And the function p of x in this case is some multiple of a sine. sine n of n pi x over a. Okay, so maybe I'll call it Pn. Alright, so those are the solutions of this problem. The solutions of this problem are very similar. They have the same boundary conditions. Right? So this is a sine because we have that the function vanishes at the endpoint. It's similar to the freezing ends boundary condition. If these were derivatives, then we would have cosines. These would start at 0 and so on. So here for non-trivial solutions, similar thing. For non-trivial solutions, we must have this constant now, the k minus L. K minus L has to be equal to negative, right? So this is like what the constant L was playing, the role that the constant L was playing. As k minus L is equal to negative m pi over b squared for m some integer positive greater or equal to 1. And I'm calling it m instead of n because these integers, they don't have to be the same. So I want to use a different name. Right? And then qn of y is going to be equal to, maybe I can put an an here. I don't think it's going to matter. Maybe bn sine of m pi y over b. Okay, so we found P and we found Q. We just need to find G, right? This gives us what? Oh, sorry, that wasn't M in the subscript here. This gives us the function f. So the function f, you have to choose two integers. You have to choose the n and you have to choose the m. They are not related, right? So for any choice of two integers, n and m greater or equal to 1, then we can define this function f n m of xy. It's just the product of P and X, Q M Y. Let me now AN and BN. Let me just call it a number A. As you know, the multiple in the F doesn't really matter, right? So in fact, let me just call them C. Okay, so because it's just not very important. Okay, just a constant that's unimportant. And here, when I multiply, I'm not going to call it c squared. I'm going to call it c again. All right. It's just an unimportant constant that's going to go away. And the Pn of x is going to be sine n pi x over a. The Qm is a sine of m pi y over b. And that's what f has to be. And m x y is equal to some constant times the product of these two signs. Interesting function, in my opinion. And one thing that's going to be important, so we found what f has to be. That's what f is. But one thing that's going to be important is to figure out what is the k, because if it shows up in, there's a few reasons, but it shows up in the equation for g, you see? So this function f that we cooked up is an eigenfunction of the Laplacian. K is the eigenvalue of this function, so that's one reason why it's important. But it also shows up in the equation for g. Right? So for us to solve this equation for g and figure out what g has to be, we need to figure out what the k was. What is the k? right? So you look at these equations here. We have L and we have K minus L. So we can find K, right? Because K, so let me write here. What is the corresponding the value of K? Well, K minus L is equal to negative m pi over b squared. That's the equation we had. So K is equal to L minus, sending L to the other side, minus m pi over b squared. And L, we had a formula for it. It was negative n pi over a squared. So this is minus n pi over a squared minus m pi over b squared. You could factor out the pi squared. I don't know if that really helps much, right? But that's what the k is. If you fix the n and the m, those two integers, then you have this constant k and m, which is minus n pi over a squared plus m pi over b squared. Right? That's k. Once you fix n and m, you chose k. And all right, and so now finding g is the one thing we have left. G of t. So g had to satisfy this differential equation. G dot dot of t is equal to what was it? It was a c squared and a k and g of t. And we have this k now, which is equal to minus c squared, all of this good stuff, n pi over a squared plus m pi over b squared times g of t. These numbers are not hugely important. You can call this whole thing together lambda n m. Okay. Squared, in fact. Let's square it. So c is a positive number, and n pi a and n pi, and you just take a square root of this thing. But the thing is that this whole thing is a positive number. The negative sign is out here. And g dot dot equal to minus lambda n m squared g of t. This is a harmonic oscillator equation. You can also solve it using the characteristic function type process, but the roots of the characteristic equation here will be purely imaginary. That's when you get a harmonic oscillator. But the important thing is that we find these solutions. G, N, M, T. It's going to be A, N, M times cosine of lambda N, M T plus B and M times sine of lambda and M T. Okay, so we have F, we have G. We can finally write out the modes of this equation. The modes of the boundary value problem are um, U and M, you choose two integers. You write T, X, Y. First to write G, this equation here. So A and M cosine lambda and M T plus B and M sine of lambda and M T. That's the G. Boy, I need more space here. Times the F. The F was the product of the signs. It had a constant C in front of it, which I said was unimportant, and I'm not going to write it. It's going to be sine of n pi x over a times sine of m pi y over b. And these are the modes of this boundary value problem. All right. So one thing I want to point out is that the frequency of the vibration is equal to the lambda and m. Okay. So the frequency. So if you want the pitch of the sound you're hearing of the vibration is, I don't want to say it's exactly the same because there's a 2 pi, but so it's in fact is lambda and m over 2 pi. Okay, and you see, as you choose these two integers, then you choose what the pitch is that the membrane is producing. Of course, in a drum you don't quite hear a pitch, but I guess maybe a xylophone is a good analogy. And one interesting thing is that there's actually different choices of N and M that will give you the same pitch. They will produce the same lambda and M. So I just want to write the remark, different choices. Oh, and here I should really write N, M greater than 1 integers. Okay, so maybe I'll put it in the purple box. Okay, so different choices of N, M may produce the same lambda and M, which then could produce the same pitch, right? So the lambda and M had an n pi over a squared and an m pi over b squared, and depending on what a and b's are, you could produce different values choosing different n's and m's. We can analyze that more carefully later. This video is pretty long, so I want to finish here. So those were the modes of the two-dimensional wave equation. On the next video, we can talk about how to solve initial value problems, and we can talk about how, in this case, different modes could generate the same pitch for the equation. All right, I'll see you in the next one.